Okay, now week 5. In this week, we have two parts. In the first part, we will conclude our learning on kinematics of a rigid body. In the second part, we will touch a little bit about kinetics of a rigid body. We will continue our study on relative motion analysis of acceleration. As mentioned in last week, in this week, we will focus on roll without slip motion. Rolling motion without slip is a common type of problem. The rigid body can be a ball, can be a cylinder, or a disc. Based on our previous study, we already know rolling motion without a slip is a general plane motion. Whatever a ball, a cylinder, or a disc, as we are studying planar kinematics, the diagram will be same. And we can use relative motion analysis of velocity and acceleration to solve a problem of rolling motion without a slip. When we studied relative velocity analysis, we know we have only one equation. And when we studied relative acceleration analysis, we know we have only one equation. In these equations, when we do analysis, we need two selected points. We already know these two selected points can be the circle center point G in this diagram and the contact point A. The contact point A is on this rigid body, but it's the contact point between this rolling rigid body and the surface. In velocity analysis, why we selected point G and point A? For point G, because it's the circle center, so the distance from this point G to the surface is always the same. So that means at point G, the velocity Vg must be horizontal because the moving path of point G is a straight line, it's horizontal. For point A, because it's the contact point between the rigid body and the surface, and we have already assumed no slipping occurs, so we know point A is the instantaneous center of zero velocity. But be careful here, we only have instantaneous center of zero velocity. We never have a point can be called an instantaneous center of zero acceleration. Now, velocity analysis And here we need a coordinate system, and this coordinate system is a conventional one. And this is the equation for relative analysis, or relative velocity analysis. This is a vector equation. And in this vector equation here, we already know VA is 0 because it's the IC point. For VG, we only have VGX, the X component of VG. But for the Y component of VG, VGY, it must be 0. So from this vector equation, we can get the relationship between Vg, actually Vgx, and omega. We watched this video before. Let me show you again. Look at the velocity. C is the IC point. C is the IC point, so at point C, the velocity is 0. And because this is IC point, so we can easily find the point B is velocity. Now, acceleration analysis. We still look at point G and point A. So firstly, point G. For point G, because we already know point G is moving past, is a horizontal straight line. So at point G, we know AG must be horizontal, and that means the y component of AG, AGY, must be 0. We only have a non-zero x component of AG, that's AGX. And how about point A, AA? For point A, actually, AAX, the x component of AA, must be 0. We only have a non-zero AAY. But why? Let's look at this diagram. And here, a rigid body is rolling forward, and we assume its angular acceleration and angular velocity, both of them clockwise. Okay, here, look at 2 points. One is A prime, point A prime, and another point is A double prime. Point A prime is a point immediately before point A. Point A is the contact point. Point A double prime, this point, is immediately after the contact point, point A. The distance from point A prime to point A is ds. And the distance from point A double prime to point A is ds. So they are same. Okay, now ds is actually very, very small, infinitesimal. And here, in this diagram, the distance of ds is exaggerated. We have already know how to do velocity analysis in this case. So we know at point A prime, at this point, velocity VA prime must be to this direction, and it's perpendicular to the line connecting point A and A prime. As similar as this, at point A double prime, this velocity VA double prime must be perpendicular to the line connecting point A and A double prime. And this time, because of the direction of this angular velocity omega, so VA double prime, this direction must be upward. But here, VA prime, this velocity is direction downward. Because the distance from A prime to A is equal to the distance from A double prime to A. So, you know, because A is the IC point, then the magnitude of VA prime and VA double prime, these two should be same. But their directions are opposite. Okay, now what can we get from this analysis? This analysis can tell us the x component of acceleration at point A must be 0 because the magnitude of VA prime is equal to the magnitude of VA double prime. But the y component of AA is not 0. It suddenly changes the direction of velocity at point A from downward at point A prime to upward at point A double prime. Okay, now we can do relative acceleration analysis. And here, that's the equation for relative acceleration analysis. And here we have AG, we have AA, alpha, and omega. And here, based on our analysis just now, we know AGY should be 0 and AAX should be 0. Okay, then rearrange the right side. Before I, we have alpha R, and before J, we have AAY minus omega square R. Compare left side and right side. We can get AGX. It should be equal to alpha R. and 0 should be equal to AAY minus omega square r. So that means AAY should be equal to omega square r. Because AGY is 0, if we know AGX, so actually we already know AG. Because AAX is 0, if we know AAY, so we actually already know AA. These two equations, AG is equal to alpha r and AA is equal to omega square r. These two can be adopted directly. In the future, when you have a rolling motion without a slip problem, you can use this conclusion directly, and this can save you a lot of time when you do analysis, when you solve a problem like that. And here I can show you some other situations. So for example, here in this diagram, you can see a rolling problem without a slip, but this time alpha is direction counterclockwise. AG and AA, they are magnitudes not changed, but AG is direction this time is negative, and AA this time is still positive. And here we based on this conventional coordinate system. A situation can be like this. And in this case, A will be the contact point, and G, the circle center, is acceleration vertical, downward. AA is acceleration horizontal. Okay, now that's AA and that's AG. Be careful of their signs. And also, we can have other three situations. AG, AA. Magnitude not changed, but be careful about their signs. And here, alpha counterclockwise, and this one alpha clockwise, and this time A is on the right side of this rolling rigid body, and here alpha counterclockwise. My previous analysis probably cannot convince you, especially about the acceleration at the contact point A. Okay, now actually I can show you a not native analysis method. And in this method, we can have two steps. In step 1, I can work out the acceleration at point G, AG, using relative analysis of velocity. to get this Vg is equal to omega r. And then I can use absolute motion analysis of acceleration. I can do time derivatives on both sides. Then I can get Ag is equal to alpha r. For this step 1, I can also use absolute motion analysis of velocity and acceleration. And here, because this is a rolling without slip problem, so the distance of the circle center point G, Sg, can be expressed using r times theta. Then I can do time derivatives on both sides for the first time and then the second time, so I can get Ag is equal to r alpha. Then in the second step, step 2, I do relative acceleration analysis. I have already worked out Ag, and then you can find Aax must be 0 and Aay must be equal to omega square r. So this time I used a rigorous calculation method and I can get the same conclusions. Aay and Ag. Now, conclusion and comparison. We are talking about rolling without slip problem. And we can do relative velocity analysis, and also we can do relative acceleration analysis, and we can work out the velocity at point G. We know the velocity at point A must be 0. And we can work out acceleration at point G, and we can work out the acceleration at point A. Again, let me highlight this point. At point A, this is the IC point, instantaneous center of zero velocity, because of no slipping occurs here. But for acceleration at point A, we only have a zero component of Aax, but Aay is not 0. Okay, now examples. In this first example, and here you can see a code wrapped up the inner hub of this sprue. So when we release this sprue, it will be going down. And here in this problem, we know its angular velocity, angular acceleration, both of these two parameters are clockwise. And here the task is to determine the acceleration of point B. For a sprue and a code, and normally we assume between this code and the sprue, no slip occurs. So this means this contact point A must be an IC point. We define this problem, and this sprue is undergoing general plane motion and no slipping at point A. So we can have a kinematics diagram. We defined a conventional coordinate system, and in this diagram here, omega, alpha, both of them are already known and they are clockwise. According to this coordinate system, omega and alpha, these two should be negative. A is the IC point. So at this point, AAX is not 0, but AAY must be 0. At point G, AGX must be 0. We only have AGY. Okay, now the target is ABX and ABY. If we know these two, we know AB. We don't know AAX and AGY at this moment. When we use vector calculation, we use relative acceleration analysis. We can assume all these parameters, these 4 parameters, positive. Now, what equations we can use for solving this problem? For solving this problem, we need 2 equations. One is about the relationship between AB and AG. And this is about the alt circle. This alt circle. And here we have ABX, ABY, 2 unknown, and here AG at this moment we don't know. And we need another equation, and this equation is about the relationship between AG and AA. And in this equation here, this equation is about the inner circle. In this equation here, we don't know AGY, we don't know AAX. Okay, because this is the vector equation. So finally, we can establish 2 scalar equations, 2 unknowns, AAX and AGY. These 2 can be solved. And then we can substitute this AGY into the first equation. Then we can solve ABX and ABY. Here, a question is it possible to solve this problem using only one equation? This equation is about the relationship between AB and AA. The answer is no. Why? Because if you have only this equation between the relationship between AB and AA, and here we don't know ABX, we don't know ABY, we don't know AAX, so 3 unknowns. one vector equation, we can solve this problem. And next will be the calculation process. And from the first equation, we can solve AGY. And also we can work out AAX. And here, because we have already got the conclusions, the conclusion can tell us AAX and AGY. So actually, we don't need this vector calculation. And if you remember the conclusions, you can express AG and AA directly, because A is a nice point. But if you don't remember the conclusion, you still can solve this problem. Just do this vector calculation, just do this relative acceleration analysis. Then in the first step, we use the second equation. We do relative acceleration analysis again. We can work out ABX, ABY. And ABX, you can see it's positive to the right side. ABY is negative, it means it's downward. So finally, we can work out the magnitude of AB, and we can work out the direction of AB. We can work out this angle theta. The second example, similar. And here, there is a gear. A gear is rolling on a gear rack. And previously, I have already mentioned, between two engaged gears, or between a gear and a gear rack, we normally assume no slipping occurs between them. So in this problem here, we already know alpha, we already know omega of this gear. And the target is the acceleration of point A here. So to find this problem, you know this gear is undergoing general plane motion and no slipping between the gear and the gear rack. So the contact point C must be the IC point. Okay, now O is the circle center, so AOX is actually AO, but AOY must be 0. ACX must be 0, and we only have ACY. And that's the conventional coordinated system. As similar as the solution in the first example, and here, again, we need two equations. The first one is about the relationship between AA and AO. And the second one is about the relationship between AO and AC. We can solve this problem using only one equation. to get the relationship between AA and AC. Okay, here, for this equation, we can solve AOX and ACY. But again, if we remember the conclusion, we actually can use the conclusion to get AO, actually AOX and ACY directly. And this can save our time because we don't need to do this relative acceleration analysis. We don't need to do this vector calculation. And then we can use AOX, substitute AOX into this equation to work out AAX and AAY directly. That's the solution. And I suggest you do a practice to work out your final answer and then compare to my solutions. Now watch this video again, and this time look at the acceleration. The acceleration at point B and you can see when B becomes the contact point, when B becomes the contact point, the direction at that point AB is vertical. Okay. Okay, finally, let's watch a video, and in this video you can see the moving path of some points on a rigid body undergoing rolling without a slip.
Many students wonder what the path of a point on a wheel rolling without slip would look like. Today we're going to explore that and a little more. We have a spool that will roll without slip on its inner radius on this track here. To track points on it, we have LEDs. So, the yellow is exactly on the inner radius of the spool, and anything inside of that will act exactly like a wheel rolling without slip. The outer points will have more interesting paths that we will also track. In order to track the motion, we will use two techniques. One of those is long exposure photography, which will just show the end paths of the lights, and the other is video post-processing, which will attempt to track the light as it moves through the video, so you can see how it rolls.
All of the curves traced will belong to the cycloid family of curves. The first curve is traced with the green LED at the spool center. Since the center of the spool should always be one inner radius from the track, the path is traced as a straight line, with slight variations from the curve of the track. The purple LED is between the spool's center and its inner radius. All such points will trace curtate cycloids, which look a bit like elongated sine curves, and will vary depending on the exact distance. The yellow LED is located exactly on the inner radius of the spool. It traces out a cycloid, where you can notice distinct cusps once every rotation. This is when the light has zero velocity, as it is at the no-slip point and instant center of the spool. The next two curves will be prolate cycloids. Prolate cycloids form for any point outside the inner radius and will have similar characteristics. First is the blue LED. Notice that the path starts to curl back on itself. The outermost path is the red LED, which looks similar to that of the blue LED. As the path loops back on itself, you can notice that at some points, this light actually has a negative x component of velocity, even though the entire spool is moving to the right. Finally, we will show all of the curves traced out together. In this way, a full family of cycloid curves can be seen, and intermediate curves are easier to imagine. This should show how seemingly simple things can contain an entire spectrum of interesting phenomena.